as the warmest on record. These 2 years record about 1.3 degrees Celsius above pre-industrial temperature. The IPCC Working Group 1 report, which came out yesterday, uses 1.1 degrees C. This is what happens when you have different data sets. There are about 5 global surface temperature data sets that are in use around the world. The 6 warmest years are all in the 6 past years, and the 10 warmest years are all this century. And beginning in 1970 up until 2015, warming followed a linear trend shown by the blue dashed line of about 0.18 degrees C per decade. But in the past 6 years, you can see that the temperature has lifted off of this line. It's looking like this year, 2021, is going to be dominated by La Nina-like temperatures, and so we're likely to see cooling. Whether we come back down onto that blue trend or not, we'll have to wait and see. But Jim Hansen, at least, former lead scientist at NASA Goddard Institute for Space Studies, felt that the past 6 years here represented more than just natural variability, that the departure off of the long-term trend actually represented an acceleration in the rate of warming. So just to make sure we're all on the same page, it is an anthropogenically enhanced greenhouse effect that is driving this warming. The greenhouse effect works where sunlight enters the atmosphere. If it encounters a bright surface, the high albedo will reflect the sunlight back off out of the atmosphere back to space. But where we get solar energy intersecting a dark surface, the dark surface will absorb that energy and then re-radiate at lower frequency, the infrared portion of the spectrum, in the form of heat. That heat is trapped. Sorry?
Sorry, I wasn't muted. I'm so sorry.
Oh, okay. This heat is trapped by a group of gases known as greenhouse gases that then re-radiate the energy in all directions, some of it back out to space and some of it back down to Earth's surface, reheating Earth's surface. As you warm the air through this process, the air holds more water vapor, so you get what's known as an amplifying feedback effect. And water vapor, in fact, is the strongest greenhouse gas. It is the most effective at trapping heat, but the water cycle tells us that the average residence time of water in the troposphere, the lower layer of the atmosphere, is only about 10 days or so. So it's really impossible for us to increase the humidity, the water vapor content artificially, other than by warming the air through some other gas, such as carbon dioxide, some other greenhouse gas. Water vapor, in fact, is so powerful that of the total greenhouse effect, it represents 36 to 70% of the entire effect, but carbon dioxide is considered responsible for about 70% of just the anthropogenic aspect of the enhanced greenhouse effect. And of course, we have other greenhouse gases, methane, nitrous oxide, fluorocarbons. We have black carbon particles, which are released when fossil fuels are incompletely combusted. Those black carbon particles act like a black body effect in the air, so they will re-radiate heat once they absorb solar radiation, and that adds to the heating budget. But then as we are reducing fossil fuels and replacing them with cleaner energy, renewable energy, we're actually reducing aerosols that had blocked some component of sunlight And so we're actually causing global brightening with cleaner air, which is allowing more sunlight in, and that works as an additional cooling effect. This is the carbon dioxide record at Mauna Loa Observatory. In the first decade or two of collection, the rate of growth was about 0.8 of a part per million per year. But in the last decade, we've seen acceleration in CO2 growth rate. It's on the order of 2.5 parts per million per year. So not only is the warming accelerating, but the principal driving gas, carbon dioxide, is its accumulation in the atmosphere is also accelerating. So over the past decade, the release of carbon dioxide, about 86% of it came from fossil fuel combustion, and another 14% came from various forms of land use, including deforestation, but also extractive agriculture, where deep plowing and turning over soils oxidizes the carbon in the soil, and soils end up releasing carbon dioxide. And on an average annual basis, this carbon dioxide will go into the atmosphere. About 46% of it will move into the atmosphere, and it will lead to global warming. About 31% of it is taken up in the terrestrial biome through photosynthesis, and about 23% of it is dissolved in the oceans, leading to ocean acidification. So this 31% taken up by the terrestrial biome is an extremely important component of managing the CO2 that we release, and unfortunately, it is under threat. This paper is one of about 4 or 5 papers, and by now there might be a few more, that report on weakening of the terrestrial biome's capacity for storing carbon. So photosynthesis removes carbon dioxide from the air, but plants also engage in respiration, which releases carbon dioxide. And photosynthesis has a thermal maximum, past which photosynthesis sharply declines, but respiration continues to increase. So because of rising temperature, this thermal maximum is beginning to degrade the sequestration of carbon by land plants. And with continued emissions, it's projected here that carbon uptake will continue to degrade, potentially reaching 50% reduction in that 31% storage capacity as early as 2040. So this effect of losing the terrestrial biosphere as a partner in managing and sequestering carbon that we release into the atmosphere is not accounted for in the nationally determined contributions of the United Nations Framework Convention on Climate Change. In other words, the national pledges to reduce emissions do not take this into account. Now, one of the important components of warming is that we are damaging the refrigeration system for the planet. And that refrigeration system is the Arctic sea ice. In the summertime, we see Arctic sea ice. Now, the surface area has reduced 50% since we were first able to measure it using satellites, 1979, 1980. And the oldest and thickest sea ice is actually almost gone now. It's down 95%. This leads to Arctic amplification because as that sea ice retreats, we expose more dark Arctic Ocean water. And we're also seeing a decline in snow cover above the Arctic Circle. So there is more dark land now able to warm up with sunlight and release infrared radiation, which is trapped. So this phenomenon is known as Arctic amplification, and the Arctic is warming 3 times faster than the global average rate of warming. And let's not forget that Greenland, one of Earth's 2 remaining continental ice sheets from the last ice age, is in the Arctic. So this is an important amplifying feedback effect, the decline of the albedo, the reflection of sunlight, and basically the refrigeration effect of the Arctic. In fact, there's an amplifying feedback that takes place here. So as temperatures rise, we see more melting of Arctic sea ice, more dark ocean is exposed, which absorbs solar radiation and releases more heat, which then raises temperature, and we get into this cycle, this feedback cycle. This is what the temperature change since the 19th century looks like. You can see that the Arctic shows the greatest amount of change on this map. And with Greenland located in the Arctic, we're able to measure the mass change. The gravitational field of Greenland is measured by the GRACE satellite. In fact, we're in our 2nd phase of the GRACE satellite. GRACE stands for Gravity Recovery and Climate Experiment. And it is recording the loss of mass from Greenland. 280 billion tons is lost annually on average, and Greenland is considered responsible for about 26% of global mean sea level rise, coming from the melting of the ice sheet there. Back to our map, we can see that the fresh water, which is streaming off of Greenland, this fresh meltwater, is collecting in the North Atlantic. In fact, temperatures in the North Atlantic are the coolest they've been since they were first measured by Ben Franklin, sailing back and forth between Europe and the colonies. And we can also see clearly the ocean warming occurring here, and the fact that continents are warming faster than oceans. And ocean warming, in fact, lags behind atmospheric warming. And as long as the air is warmer than the ocean will continue to take up heat from the atmosphere, and in so doing, thermally expand. But because the oceans are so deep and circulating that heat down into the abyss takes many, many centuries, the warmer air will drive thermal expansion by the ocean for over 1,000 years, meaning that sea level rise is unstoppable, and it's, from a human point of view, it's perpetual. Now, by rapidly decreasing our emissions, it is thought to be possible to stabilize climate at a fixed temperature, and the current goal is to stop warming at 1.5 degrees Celsius. Sea level rise will nonetheless continue, but at least by stabilizing climate, the rate of thermal expansion will decrease with time. This is heat storage by the ocean. Light blue is the upper 700 meters, and dark blue is down to 2 kilometers. And in fact, the oceans in 2020 recorded the highest temperatures we have yet to measure. And since 1955, more than 90% of the excess heat retained by anthropogenic greenhouse gas release has been absorbed by the oceans. In fact, if the oceans had not absorbed the excess heat that we had caused to accumulate, Earth's land surface would already be too hot for human existence. And thermal expansion in the sea level budget accounts for about 1/3 of global mean sea level rise. Now that fresh water in the North Atlantic is slowing the conveyor belt, the global surface circulation system, where warm water flows out of the Pacific through the Indian Ocean and up through the Atlantic. This warm water would typically descend when it reaches the North Atlantic. As this water in the form of the Gulf Stream, which is one component of what's known as the Atlantic Meridional Overturning Circulation, or AMOC, it releases heat as it travels to the north. That heat makes the climate in the northern European states much more moderate than it would be otherwise. And there is heat also that descends down to deeper water with the descending surface current. The reason the surface current descends is because there is evaporation that takes place as it travels to the north. It becomes saltier and saltier as it loses the H2O, and it becomes so dense that it eventually descends down through the Atlantic Ocean water column, not quite to the bottom, and it actually flows back then at depth back down to the south. So that's why it's a conveyor belt. And it's an important mechanism that buries heat in the deep ocean. But this current has slowed, and in fact, a paper came out last week that conjectured that we might actually be seeing the beginning of a breakdown of this current. The amount of slowing is on the order of 15%, documented by several earlier papers. And the transport of warm water through the Atlantic has decreased. The transport of heat out of the tropics to the north has decreased. There's fear that tropical Atlantic water will heat up and that will feed more rapid intensification of tropical cyclones and hurricanes. And also the decrease in warm water moving through the South Atlantic is partially responsible for increased drought. And we see drought hitting the Congo and Amazon rainforests. Much of that drought is due to deforestation, where you're converting rainforest to open savanna, and just warming air temperatures in general. The evapotranspiration mechanism over these rainforests tends to produce its own precipitation, and as we deforest and as there are increasing wildfires, we see a reduction in precipitation. In fact, it's now been concluded that the Amazon is perhaps tipped over into a net greenhouse gas source rather than a sink. The Amazon basin contains more than half of all tropical rainforest, but it is threatened and stressed with logging, mining, hunting, deforestation. The multiple rivers in the Amazon are dammed. The reservoirs that result release methane and nitrous oxide into the air. There is strong drought. There is tree mortality. And in fact, over the past decade, the Amazon lost as much as 1/3 of all its biomass. And so in the past decade, the Brazilian portion of the Amazon basin gave off about 18 billion tons of carbon dioxide equivalent to the atmosphere, but only drew down 15 billion tons. And so it's now likely that the Amazon is a net source of greenhouse gas emissions. And as I mentioned earlier, there are other papers which evaluate the terrestrial biome carbon sequestration process and are finding a breakdown in the ability of continental photosynthesis to effectively remove and store carbon. And as the surface current has slowed, we have seen heat build up in the Southern Ocean, and strong ocean warming around Antarctica has accelerated melting in Antarctica, which is now losing a little more than half of the mass that is lost from Greenland. Melting from Antarctica represents about 14% of global mean sea level rise. And this area in particular, the dark red here, is a set of glaciers which are thought to be an irreversible retreat, especially the Pine Island and Thwaites glaciers. These, in fact, are losing their floating ice shelves and are flowing into the ocean. The Pine Island Glacier has accelerated from 2 to 3 kilometers per year to 5 kilometers per year rate of flow into the ocean. These floating ice shelves act as a buffering system to keep the main body of ice off the ocean, but the floating ice shelves themselves are melting, not only from surface melting, but also warm water trapped underneath. And as those floating ice shelves unpin from the bottom, from the seafloor on which they're grounded, there's nothing then to hold back the land ice from flowing rapidly into the ocean. We also have a system. So we've been talking about connected systems from all the way from the Arctic to the Antarctic, and how there are multiple impacts from sea level rise to storminess to changes in our terrestrial biome. All of these connected through this complex system. We also have atmospheric system, and so it's important to understand the atmospheric system. There is excess heat hitting the equatorial region from most direct sunlight. That heat is moved towards the poles through a series of circulation cells in the atmosphere. Very simplistically, each of the two hemispheres, the northern and southern hemisphere, have a Hadley cell, a Ferrel cell, and a polar cell. And as heat moves to the north, in the northern hemisphere, the Coriolis force will turn it to the right, and it will become one of the 2 or 3 jet streams. Now, this atmospheric circulation is driven by the temperature gradient, the difference in temperature between the Arctic and the equator. But with the Arctic amplification leading to more rapid warming, that temperature gradient is decreased, and we see the circulation system potentially decreasing as well. Now, what you're looking at here is the temperate jet stream in red, and a normal, healthy, vigorous jet stream is a very linear body or river of air at high altitude. But more and more, we are seeing these instabilities. We're seeing slowing of the jet stream, and we see these large meanders developing in the jet stream. And where you have a large meander, like you see here, Arctic air can be pulled. Weather events of agricultural losses due to cold weather, and record-setting snowfall. And where you have a meander up into the Arctic, we are pulling tropical air to the north, and we'll see heat waves. You may have heard about the heat dome that developed over the Pacific Northwest in June. That was one of these meanders that developed extremely hot air that was stationary for a week or more. And in addition to exchanging these extreme temperature conditions, the whole thing moves slower. So you get an extreme weather event that lingers and lasts longer than it would have historically. And so from a strong jet stream driven by a steep temperature gradient between the Arctic and the equator, we now have greater occurrence of a weak jet stream. And this leads to record heat waves as well as record cold and snow. Now, this is partially reflected in extreme weather losses. And last year, 2020, the US weather disasters set a new record. We saw 22 separate weather disasters in the United States that caused at least $1 billion in losses. This was a record. The previous record was 16 events, which occurred twice in the past decade. And last year we saw $95 billion in damage. And over the last 30 or 40 years, I guess, we've seen about $2 trillion in damage due to extreme weather events. And you can see from 1980 up to present day, drought, freezing, tropical cyclones, wildfire, etc., flooding. You can see these different types of weather disasters occurring with greater and greater frequency. And you've heard, no doubt, about heat waves. Heat waves are the most fatal form of extreme weather. 37% of warm season heat related deaths are now attributed to climate change. And this increased mortality is evident on every continent and constitutes dozens to hundreds of deaths per year in many locations. This paper came out in May, and it studied the heat-related mortality at 732 separate locations in 43 countries. Heat is considered the invisible threat. And remarkably, over the 20th century, we actually saw a steep drop in heat-related mortality of about 75% around 1960. Almost the entire decline occurred then, and you might guess why that is. It's because of the spread of residential air conditioning. Essentially, the entire decline in hot day related fatalities can be attributed to the diffusion of residential air conditioning. And the present value of US consumer spending on air conditioning is estimated at between $85 and $188 billion. However, climate change is disrupting power grids around the country, and grid failures have increased 60% since 2015 just in the US. The potential for critical infrastructure failures during extreme weather events is increasing, and the crutch of air conditioning is becoming less reliable over time. When we get compound events, grid failure plus a heat wave, the extreme heat outside as well as inside the buildings can reach dangerously high levels. And compound events expose 68 to 100% of an urban population to elevated risk of heat exhaustion or heat stroke. In fact, major US cities experienced 3 times as many heat waves in the past decade as during the 1960s. The heat season, in fact, has lengthened by about a month and a half, and extreme heat dramatically increases the chances of preterm births. This correlation has been documented. Now, unfortunately, the most recent chapters of racism in the United States include redlining. Redlining was an exercise in the 1920s and 30s where federally backed mortgages were not made available to certain low-income neighborhoods where persons of color lived, and federal agents working with local banks actually created maps and drew red lines around neighborhoods of color. That has translated up to today. Those same neighborhoods have reduced shade. There is less tree cover. The average person of color lives with higher heat intensity than non-Hispanic whites in all but 6 of the 175 largest urbanized areas in the continental US. There's a similar pattern for people in households that are below the poverty line compared to over 2 times the poverty line. So urban heat health issues are amplified in neighborhoods of color and neighborhoods of lower income because of this pervasive racism of the last couple of centuries in the US. We're also finding a number of papers coming out telling us about heat and humidity, the combination of the two. Was the emergence of heat and humidity too severe for human tolerance? Business as usual will lead to super and ultra extreme heat waves in the Middle East and North Africa. Deadly heat waves projected in the densely populated agricultural regions of South Asia. And escalating global exposure to compound heat humidity extremes with warming. So combined heat and humidity is known as wet bulb temperature. And 35 degrees C wet bulb temperature marks the human physiological limit. At this point, the human body is unable to offload heat and begins to experience heat-related disease. Parts of the subtropics are very close to the 35 degrees C survivability limit already, and have already reached this limit over both sea and land. Severe mortality, however, can occur at much lower values. For example, the deadly 2003 European heat wave and the 2010 Russian heat wave experienced wet bulb temperatures no greater than 28 degrees Celsius. Warming of about 1 degree C above pre-industrial levels has already increased the population annually exposed to at least 1 day with wet bulb temperature of 33 degrees C, from 97 million people to 250 million people. This will increase to 500 million people with 1.5 degrees C of global warming, 750 million people with 2 degrees of global warming, and over 1 billion people when and if we reach 3 degrees of global warming. Now here is a model output where wet bulb temperature is 31 degrees C at warming of 1.5 degrees Celsius. Now this is the United Nations Framework Convention on Climate Change target. It's severely in doubt. We are currently on a greenhouse gas emissions pathway to over 3 degrees C of global warming, but 1.5 C is the target for reducing emissions. It's still possible, although it is becoming more and more unlikely. And what we see is a wet bulb temperature of 31 degrees C occurring 100 days per year in Southeast Asia and the Middle East, and about 1 day per year on the US East Coast and mid-continent areas. When global temperature reaches 2 degrees Celsius, we're looking at an average of 10 days per year of these extremely deadly wet bulb temperatures occurring east of the Mississippi, and these basically intolerable, unlivable conditions in Southeast Asia, India, and the Middle East. And our current trajectory of warming 3 degrees Celsius, we're looking at the continental US catching up with North Africa, the Middle East, and Southeast Asia at 100 or over 100 days per year of these extremely dangerous wet bulb temperatures. Another paper, which I encourage you to read, I believe it's open access, is called Future of the Human Climate Niche by the Proceedings of the National Academy of Sciences. Identifies that today, these black areas in the Central Sahara and along the Red Sea represent 0.8% of the land surface. These are areas considered too hot for human existence. And by 2070, on our current trajectory of emissions, we're looking at this expanding to potentially 1/5 of all land surface, 19% of the land surface within 50 years, too hot for human existence. This is likely to displace 1/3 of humanity, and we will see what's estimated to be 1 billion people displaced for every additional 1 degree Celsius of global warming above where we are right now, which is warming a little more than 1 degree C above background. We also have a freshwater crisis. We are withdrawing freshwater from our aquifers at rates that exceed natural recharge. In the continental US, largely for irrigation, we are pulling water from aquifers 17% more than annual recharge is able to replace. And in China, it's 22%. The Middle East and North Africa, it's even higher. So we are using up our primary stores of fresh water. This is the very definition of unsustainability, especially since by mid-century, water demand is projected to grow by 55%. Already, 17 nations are under extremely high water stress, meaning they are using almost all the water they have every year. And right here in southern India is the 10 million person city of Chennai. 2 years ago, Chennai ran out of water. All 4 reservoirs feeding that city dried up. We also have impacts to food. As the level of carbon dioxide in the air increases, rice, soy, corn, and wheat put more metabolic energy into the stalk and the leaf and less into the food component and less into the seed. These staples grown under higher CO2 have less micronutrients, zinc, vitamin B complex, and iron, and they have less protein being replaced with carbohydrate. This effect within 30 years is expected to lead to an additional 300 million people being malnourished and 1.5 billion women and children likely to have anemia. Let's look at wheat. Currently, global wheat provides 20% of all human protein. The yield is threatened by drought, flood, and higher carbon dioxide. By 2050, the demand is expected to increase by 60%, but the actual yield to decline by 15%. food shortages, malnutrition, and water shortages, and displacement by intolerable weather conditions, especially heat, can lead to violent conflict, especially at border zones. And there is a study that identified an intense drought at the beginning of this century that hit the Middle East. This collapsed the farming economy of Syria, drove these families into urban areas of Aleppo and Homs and Damascus, where the corrupt regime of President Bashar al-Assad was evident in the form of the lack of government services. The young men created a rebel force, started a civil war in Syria. Coalition forces were pushing al-Qaeda out of Iraq and Afghanistan. They found safe haven in Syria. And, we saw a spin up of extremely violent conditions, which led to 4 million people moving out of Syria. Those who moved into the EU led to a rise in authoritarian political figures, ultimately leading to the United Kingdom, or Brexit, actually England, not the United Kingdom, seceding from the European Union. And so you change politics, and the trend is to an increase in authoritarian figures when you have a large population of migrants, or in this case, climate refugees. So disease, environmental damage, climate change, and human inequality form an amplifying feedback, especially in this tropical region shown with the hotter colors. Disadvantaged groups suffer disproportionately. This results in greater inequality. And we see this expressed in the form of income as well. The ratio between the income of the richest and poorest 10% is 25% larger than it would be in a world without global warming. Now, at the same time, we're seeing biodiversity loss, largely because of human consumption habits. Since the dawn of civilization, humanity has caused the loss of 83% of all wild mammals and half of all wild plants. Humans have altered up to 70% of the world's lands. 40% of the world's original forests have been eliminated. Oceans are hotter, more acidic, and dissolved oxygen will continue to decrease for many centuries as oceans continue to thermally equilibrate with the atmosphere and warm. And by mid-century, models indicate 99% of coral reefs are projected to experience annual bleaching. An average of 1.3 species go extinct every year, which is over 15 times the rate of extinction prior to the 16th century. 86% of all land mammals are now livestock or humans. Since 1970, food crop production increased 300%, and half of all agriculture expansion has come at the expense of forests. We're deforesting the planet at the rate of 3 football fields per minute, largely to raise cattle and the grain to feed them. 43% of all ice and desert-free land, 2/3 of all freshwater use is for food production. Over 80% of farmland is used for livestock, but it produces just 18% of food calories and 37% of protein. Cattle and the grain they eat use 1/3 of available land surface on this planet and 16% of all available fresh water. 1/3 of worldwide grain production is to feed cows. Producing beef generates 100 times more greenhouse gas than plant-based food. And deforestation and warming air has brought us into the new era of pandemics. 70% of emerging diseases and almost all known pandemics are zoonoses. In other words, they're caused by microbes carried by animals that spill over into the human community. This emergence of pandemics is driven by habitat loss, agricultural practices such as concentrated animal feeding operations, and climate change. The climate change connection is expanded vector range, extreme weather events which drive microbes and pathogenic organisms into contact with the human community, displacement of the human community and weakened human immunity during episodes of heat and during episodes of other types of extreme weather. And the loss of habitat, deforestation, agricultural expansion, and the wildlife trade exposes pathogens that have been in equilibrium with their wild communities, but now brings them into human communities. There's been an exponential rise in consumption and trade, and this has led to emerging diseases from developing countries. The good news is that clean energy has become cheap. Over the past decade, we've seen an accelerating decline in the cost of solar, wind, and batteries. Renewable energy use is accelerating. This is gigawatts of renewable energy additions every year since 2011. Last year, renewable energy generation grew by 45%, the fastest rate in 2 decades. China accounted for 80% of new solar and wind installations, and renewable energy will account for 90% of new global power capacity this year and next year, it is projected. This momentum will continue so long as critical minerals continue to be available. But the world is on course to use ever more energy. The current surge of renewables is some cause for hope, but only a modest one. It's projected that carbon emissions are set to soar next year. In fact, recovery from the COVID recession has put the oil industry back in business. We see Shell reporting billion-dollar profits, Exxon, BP, Chevron, all the oil industry and in fact coal industry are seeing a return to profitability. Carbon emissions are projected to increase this year by the second highest rate in history. Global economic output in 2021 is expected to rebound more than 2% higher than 2019 pre-COVID. And this year, the demand for all fossil fuels is already growing significantly. Coal demand is projected to increase by 60%. This is more than the demand for all renewables combined. Emissions are projected to increase by 5% this year, which reverses 80% of the emissions drop during the depth of COVID last year. At the end of this year, it's projected that greenhouse gas emissions end up barely 1% below 2019 emissions levels. And next year, it'll probably be even stronger emissions as emerging economies are driving energy demand back above 2019 levels. Global energy-related carbon dioxide emissions are headed for their second highest annual increase ever. And the fact is that nearly 1 billion people still don't have access to electricity. They desperately need energy, and fossil fuels are often the only sources available to them. This is the history of carbon dioxide emissions since 1850. And in order to stop warming at 1.5 degrees Celsius, we need to have 0 emissions within 30 years. If we want to stop warming at 2 degrees C, we get an extra 15 years. This is going to require nearly a 50% reduction in emissions by the end of this decade alone. Then we will be stuck with a warmer climate that is extremely dangerous, and we need to remove CO2 from the air. And as we've learned, photosynthesis in the terrestrial biome is not going to be a strong partner in this. So there are lots of ways to stop global warming. A zero emissions electrical grid. We need to get rid of thousands of factories and power plants that have to be renovated. and cleaned. Existing fossil fuel infrastructure must be decommissioned before its lifetime. We need zero emission buildings with retrofits of their energy and efficiency, a revolution in our agriculture system, a reduction of meat consumption and an increase in plant-based proteins. And we need social tipping points as well. Society has to recognize the immoral nature of fossil fuels, and our consumer lifestyle needs to come to an end. So with that, I will end. I'm sorry I've gone so long, but thank you for your time. And if anybody wants to stick around, I'll be happy to take any questions. Thank you very much.